Okay, good morning or afternoon or evening, participants in Parity from Home workshop. It's my great pleasure to be here virtually to share my recent work, which is about the chiral gradation waves during inflation and reheating. And I'm Chao Chen. I'm a faculty from the Jiangsu University of Science and Technology. And this work is finished with the two other guys, Chen Jiefu, associate professor from Anhui Normal University, and Yi Wang, a professor from Hong Kong University of Science and Technology. The outline of my talk is simple. First, I'm gonna talk about the parity in nature, and then move to the chiral gradation wave generated from inflation and the reheating. At last, I will summarize my talk. Okay, we already know that the parity is broken in wave inductions, which tells that our nature distinguishes left and right hands in the matter fields. Then a question naturally arises, does gravity conserve the parity? I believe all of you know the answer. Einstein generated parity conserved. I can give you an example. For gravitational waves predicted in general relativity, which are massless gravitons, they have two helices, right? Also in the left and right-handed polarization states, they defined in this way. And as gravitational wave pass through the space-time, different polarization states cause distinct distortion of the space-time, which can be observed through the effects on the test mass, as illustrated in the following animation. And the dashed line acts as the virtual mirror. And these two polarization states are parity-symmetric, and they have the same amplitudes and velocities. Then we can say the gravitational wave in general relativity are parity-symmetric. Although Einstein GR is parity-symmetric, but we have a lot of the tensions of Einstein's GR, that is modified gravity, which predicts many gravitational parity-violation terms. In this paper, we only focus on the linear chiral gravitational waves, which means we only have the two edge gravitational waves in the action. And in order to construct parity-violation terms, we need totally a symmetric term, symmetric symbol, epsilon RJK here. So then you would have these four common combinations in the action. And according to the variation principle, you can get the equation of motion for the chiral gravitational waves. And the coupling function F1, F2 to the F5, they are functions of cosmic time t. And it turns out the first term, the blue one, generate additional term in the second time derivative and the first time derivative, which will cause the kinetic instability. And the blue one contribute to the gradient term, which causes the gradient instability of the gravitational waves. Only the last two terms, they are healthy. And we also notice that the last term, the red one, has the lowest dimension. So we expect it's least expressed in the effective field theory. So in this paper, we just focus on the last term. And also we consider the gravitational parity violation happened in the early universe, that is during inflation. So we ask such a question: is there any significant signature of the parity violation in the probability of gravitational waves? And in general, the coupling function F5 is a function of scalar field phi and its time derivative. Here we regard the phi as an inflaton. And we also consider the case F is just proportional to h dot, because h dot characterizes the slow inflation because phi dot phi dot is related to slope parameter, which is the most important parameter describing the inflation. And secondly, the phi dot generally arises in parity-violating extension of the teleparallel gravity, so we consider such form. And in this paper, we aim to investigate the phenomenology from this action. Okay, so we have the standard of the linear gravitational waves and plus the parity-violation term. Okay, and the A here is a scale factor, comes from this spectral derivative, and the big lambda is the anti-scale of this parity-violation term. Okay, when the lambda is smaller, this term, the effects of this term becomes more significant. According to the variation principle, we can get the equation motion for the chiral gravitational waves, and we get this one, and the parity-violation term here appears in the gradient term, and the lambda A could be +1 and -1 for the right-handed and the left-handed polarization respectively. So you might expect the tachyonic instability happen during inflation and reheating. But as we demonstrate later, if we work in the so-called no backreaction regime, there are no tachyonic instability happening in inflation, but we have a tachyonic instability happening during reheating. I will explain this later. So now we have the equation motion for chiral gravitational wave at the background evolution. So we can numerically solve them and get full spectrum of the chiral gravitational waves. But before that, we can make some qualitative analysis. Observing this parity-violation term, we know that this term induces smaller sound speed for the right-handed modes, right? And so this right-handed mode is frozen earlier than the left-handed mode. So this means the amplitude of the right-handed mode is relatively larger, right, as illustrated in this plot. Okay, and accordingly, if we apply the step approximation to this equation motion, and we can get an analysis solution, which is expressed in terms of Kuma function of the second kind, and we can get the power spectrum for each polarization, and they're different only by this exponential factor, and this factor, the power, is determined by this eta. Eta is also determined by the inflaton velocity. Okay, because inflaton velocity is generally increased during the slower parameter, so we expect the power spectrum, the total power spectrum of the gravitational waves exhibit the blue tiers, and the chirality of the gravitational wave is described by this ratio between the different the difference of the polarization, and it also depends on the eta parameter. Okay, it also excited the blue tiers. Okay. And for the numerical calculation, we consider the typical inflation model, so-called the E model alpha attractive potential. Okay, then we run the numerical calculation, get the power spectrum, and the spectrum index NT and the chirality, and they all displays the blue tiers, right, as we mentioned before. And we know that the chiral gravitational wave also induce a distinct angular power spectrum in CMB. So we also calculate the BB spectrum, EB spectrum, and the TB spectrum. And this dashed curve refers to the sensitivity curve predicted by LiteBIRD. So it hopefully for LiteBIRD to observe such chiral gravitational wave in the future. But we didn't observe any significant growth from the tachyonic instability because it doesn't happen during inflation, because we do not have a small enough any scale of this parity-violation term, because we only work in the no backreaction regime. And I will explain this in the next slides. During inflation, the inflaton field oscillates around the minimal potential, which can be approximated to the quadratic potential. And then we can solve the inflaton far field in terms of the sinusoidal function. And it's convenient to rewrite the equation motion of the chiral gravitational wave in the harmonic-like form. And the effective friction omega square is determined by the energy scale of the parity-violating term and the K mode. Okay, so because this omega square oscillates with a decreasing amplitude, so you can trigger the tachyonic instability for the subhorizon mode when it becomes omega square becomes negative, and followed by its inflationary sections because the universe is expanding, right? Because the scale factor appears in the denominator, so you have the decreasing tachyonic instability. So we expect that there should be a peak in the gravitational wave energy spectrum at some moment, right? So we worry about if this peaked energy spectrum would expect the background evolution. This is the backreaction issue. But unfortunately, we're not smart enough. So in this paper, we only work in so-called the no backreaction regime. Okay. And also, modes with very small or large k only express the weak or no tachyonic instability, resulting in the bump-like gravitational spectrum in the end. And then in our paper, we also provided the WKB calculation of this particle production during reheating. So please go to the appendix in our paper and see the details in calculation. And according to our numerical calculations, as shown in this figure, this is the power spectrum for two polarizations for a fixed k after inflation. And you can observe the growth of the power spectrum. This is due to the tachyonic instability. And also there is a peak. At this moment, we require the energy density of the gravitational wave is much smaller than the background energy. Rho GW over the 3h square and the m Planck square is smaller than 0.1. We call this no background region. Okay. After this peak, the gravitational wave decay at 0. So the power spectrum is just decay as the 1 over h square. Okay. This is the standard case. Okay. So we found that this no background regime provides a low bound on this energy scale of the parity-violating term. And we are interested in the observed gravitational wave energy spectrum. We applied the standard formalism to relate the early gravitational wave spectrum to the current gravitational wave energy spectrum. We also know that this also depends on the reheating history, which is described by the duration, the e-14 number of the reheating process, and also the equation state parameter during reheating. Because we have this approximate quadratic potential, so we only have the early method dominant error. So the equation state parameter W is 0. So we only have the single free parameter, that is the e-14 number for the reheating process. And then we can see that the parity-violating gravitational wave is very high frequency. It's GHz, and the dashed curve is the sensitivity curve predicted by resonant cavity. So in future is observable by these experiments for such high frequency gravitational waves. And in this plot, we vary the e-14 of the reheating process, and we get the different power spectrum. Okay, and yeah, it's also satisfied the BBN constraint. Okay, and last, I summarize my talk. Firstly, we studied the correlation wave from inflation through the reheating, and we showed that the CMB and the resonant cavity experiments provided a unique prop of the energy scale of the gravitational wave parity-violating and also the reheating history. And in the future, it's also interesting to investigate backreaction effects of the gravitational wave on the reheating phase. And also it's very interesting to consider the concrete reheating mechanism. Okay, thank you for your listening. I will stop here and take questions.